Hey everyone, so my name is Christiane and I'm here to give you a little lecture on ultrasound artifacts. I gave this lecture last week to my colleagues at Boston Children's Hospital and Harvard Medical School, and I'm just repeating it here. So I'm basing this talk off an article that I found in the Radiographics Journal, and the title is pretty simple, it's just Ultrasound Artifacts. It was written by Myra Feldman, she's an MD, and her colleagues. I found, so this was written in 2009, but it's still a good reference to use because the physics of ultrasound hasn't changed and the artifacts haven't changed as a result. So this paper is a good reference if you are, working with ultrasound and looking at an image and thinking like, what is this artifact that I'm seeing? Or is it an artifact? Is it something real? You can always refer to this paper. So I'm just going to go into a little bit of background on ultrasound before I dive into the artifacts, because we have to know what it is and how it works. So ultrasound uses sound to look inside the body. The image is based on physical properties of pulse formation. That includes the propagation of sound in matter, the interaction of sound with reflective interfaces, and echo detection and processing within the transducer. So an artifact is basically any part of an image that does not accurately represent the anatomic structure present. So understanding ultrasound means understanding wave properties, which we'll go into, and then understanding how the waves are generated using the transducer. So ultrasound, as I mentioned, is an acoustic energy in the form of waves having a frequency above the human hearing range. Or maybe I didn't say that, but I'm saying it now. So the human hearing range is about 2 Hz to 20 kHz, and the diagnostic ultrasound is about 2 MHz to 15 MHz. So we're well above the human hearing range. And then, of course, at both ends you have infrasound and again ultrasound over here. Ultrasound is a longitudinal mechanical wave. The particle displacement is therefore parallel to the wave. So this is a longitudinal wave here. You can see these this cluster of particles here, and then you can see like this separation of particles. You can also represent this in a waveform, which I've done down here as well. So the cluster of particles is basically this, and that occurs during compression. So when the particles are close together, they create a positive pressure amplitude variation. And if the particles are far apart from each other, they create a rarefaction, which corresponds to the negative pressure amplitude. Sorry. So just to go into a little bit of background, so this is so one cycle is basically the length of one positive and negative deflection of the wave. The period is the length of time to complete that cycle. Then you have the frequency, which is basically the number of cycles per second. It's measured in units of hertz here. So in 1 second, there's been 2 cycles. So the frequency is 2 cycles per second. And when I refer to frequency, sometimes I'll say like high and low frequency. So if I say higher frequency, that just means more cycles per second, as you can see here. So the chances of this wave hitting this little red dot are pretty good because of how the wave keeps interacting with matter. But because it does that, because it keeps interacting with matter, chances are it will hit something, which is good because the resolution will be better. But the downside is it will penetrate less into that matter. Then when I look at lower frequency, I'm referring to less cycles per second. So the chances of this wave hitting this little red dot here aren't as high as the chances of the high frequency wave hitting the red dot. So this means that the resolution is going to be worse, but it's going to be able to penetrate deeper because it doesn't interact with matter as much. Then we have the amplitude of the wave, which is basically the height of the wave. Sometimes amplitude can be referred to as the power. Then we have the wavelength, which is basically the distance between 2 similar points on the is the distance between two similar points on the wave. So in this case, I've chosen these point. This point here and this point here. Similarly, you can choose this point here, this point here. So basically that's the wavelength, just between two similar points. And the wavelength, as I mentioned down here, is related to frequency through the speed of sound. So this is a really common equation that you'll see often. So the speed of sound is equal to the wavelength times the frequency. And the velocity itself is determined by the material. So the velocity here, c, is equal to the square root of b, which is the bulk modulus, over the density of the matter. So the bulk modulus b is basically, it just measures the stiffness of the medium and its resistance to being compressed. So that has more to do with the medium. Then of course there's types of interference. So in this case we have this wave up here and this wave down here. They're perfectly in sync, and of course when they come in contact with each other and they overlap, they're going to have 2 times the amplitude. So that's constructive interference. Then you also have destructive interference. So basically it's when the waves are perfectly half a wavelength out of phase, so lambda divided by 2, and that's known as destructive interference. So you'll have this, basically this flat line. There won't be any resultant wave. The intensity is just basically the rate at which the ultrasound energy is applied to specific tissue. It's important with respect to producing biological effects and safety, and also the intensity at the transducer surface is measured in milliwatts per centimeter squared. So when we talk about wave interaction with matter, we want to think of the acoustic impedance. So this is the Z here, which is equal to the density of the material times the sound. So it has everything to do with the material. You have the reflection factor, which is basically the fraction of sound intensity reflected. So it's pretty obvious, but you have your incident wave here, and then some of it will be transmitted and some of it will be reflected. And this is the equation here, the reflective index, which is basically all of this. And it's it actually makes perfect sense, because if you have, say, a material, say Z1 is bone and Z2 is air, chances are that almost all of the sound is going to be reflected off the bone and it will bounce back. So if Z1 is as high, then basically and Z2 is low, then the Z2s will basically go away because they're air and the density is quite low. So the reflective index will basically be equal to Z1 squared over Z1 squared, which will be equal to 1, which indicates that all of the sound has been reflected. So that makes sense. This equation makes sense. So the reflective index is low when the materials have similar Z, and highest when materials have different Z, as I mentioned before. And the transmission is basically just the opposite of the reflection. So it's the sound intensity that penetrates. So as I mentioned, this part down here. So the transmission index is 1 minus Ri, which is the reflective index. And it's the opposite. So it's highest when materials have similar Z and low when materials have very different Z. This will become more important later when we're talking about the artifacts. I just wanted to go over the background. This may be trivial to some of you, but you'll need it later when we're learning about the artifacts. So this is refraction, which is basically the change in direction of transmission, and the angle depends on the difference in the speed of sound between the two mediums. So if the speed of sound is greater in this material here versus this material, the angle will be greater. And then you have scattering. So this occurs in objects within tissue similar than the size of the wavelength, or possibly smaller. So you have kind of 2 types of scattering. You have non-specular diffuse reflection, which is over here, and then you also have tissue interactions And so this is for objects that are a lot smaller than the wavelength. So now we have to talk about how the waves are formed, because some of the artifacts actually occur in the device that is used, so the transducer. So this is just, I'm going to give a very basic overview of the transducer anatomy. So first of all, these are what transducers look like. You may have seen them before. There's different types, and they each serve a different purpose. But most importantly, you know, as a physicist, it's important to know that the selection of transducer and what it depends on. So if you're looking at superficial vessels and organs, you know, with a depth of like 1 to 3 centimeters, or for intraoperative imaging, then you want to use a high frequency, as I mentioned before. So if you have high frequency, you're not going to penetrate as much, and your resolution is going to be better. But if you want to look at deeper structures, like in the abdomen or pelvis, like 12 to 15 centimeters, then you want to use a lower frequency. And if you recall from that previous slide, when you have a lower frequency, it will penetrate further, although your resolution won't be as good. So this is my diagram of the transducer, not as appealing as the actual transducers, but so this is the coaxial cable here, this part. You can see that over here as well. It's used to transmit and receive. And then, actually, interestingly, the transducer will listen 99% of the time and talk 1% of the time. So what does that mean? It means it transmits 1% of the time, and then it receives signal 99% of the time. That was an interesting fact that I learned. And then you have the plastic casing, which you can also see here. And then you have everything inside. So you have the metal shield. Oops, sorry, my cursor. The metal shield kind of encases everything. You have the acoustic absorber here, so this will just absorb any of the signal that bounces back. You also have the backing block, which is dampening. I don't talk about that in this lecture. I might give another lecture about ultrasound and just the anatomy of the transducer, because I think that's important. But the most important thing for this lecture is the piezoelectric element, this part here. And then you also have the matching layer, which is important too, and I'll talk a little bit about that. So the piezoelectric crystals, which I'll explain, I'll show a diagram in a moment. The piezoelectric crystals, or ceramic, are in the transducer. They have, what happens is there's like some sort of physical deformation, and during this physical deformation, they can convert electrical energy into sound, which is mechanical, or they can convert mechanical pressure into electrical energy. Sometimes the material is natural, like quartz, and most of the time it's artificial, like PZT, which I've found is the most common. So lead, zirconate, titanate. And it's characterized by molecular arrangements of the dipoles. So when mechanically compressed by applied pressure, the alignment of the dipoles is disturbed from the equilibrium, and this will cause some charge imbalance to be distributed, and the potential difference is created across the element to produce a mechanical wave that's proportional to the pressure amplitude. So what does that all mean? So basically, if you have the piezoelectric element here, whoops, this is it, and let's say we have two different materials here. So the red and the sort of brown, light brown, represent two different materials. So we'll have, say, oxygen and silicon. So they're going to create a dipole because oxygen is more negative, so it wants to hold on to its electrons a little bit more. So the green will be the oxygen and the red will be the silicon. So in each kind of lattice here, you have this kind of configuration here. It's like a hexagon. So you have your oxygen and your silicon, and then you have your center charge here, which right now is neutral, since they're all equidistant. Then if you compress it, you have the silicon, which you're going to move to the right, well, to the left, and then to the right, and this one's going to move up, and then you have the oxygen here, which is going to move down. And you also have the oxygen at the side here, which is going to going to create a charge imbalance. Oops. So all the positive charges are going to go to the top, and the negative ones are going to go to the bottom. And so if we think about it like this, you have, all the positive charges, all the negative charges, and you combine them, you'll have something neutral. And then when you compress it, basically the crystal is still neutral overall, but all those positive charges that I talked about are going to move to the top, and then you have all the negative ones that move to the bottom. And basically, if I show kind of in a different way, the distribution of these charges are going to cause these pressure waves to occur, and that's what you want, basically, to form your signal. So the cut of the piezoelectric thickness is 1/2 the wavelength. So for a thick transducer, you're going to have a lower frequency, and for a thin transducer, you're going to have a higher frequency. Then you also have the matching layer. So this is where some of the old physics stuff comes in. So you have the interface between the transducer element and the tissue. So this little layer right here. And that's going to minimize the acoustic impedance. And the cut for this is basically 1/4 the wavelength. And why is it that? It's because over here, if you have wave R2, that's, well, you have R1 and then you have R2 coming in. If R2 bounces off this part here, then it's going to be exactly half a wavelength out of phase with R1. And so what's that going to do? It's going to cause destructive interference. So you're not going to get a signal back. And that's good because these are the waves that are trying to get through, but they haven't been able to, and they're going to bounce back into the transducer. And we want to avoid having that signal bounce back. So that's why the matching layer is there, and that's why it's cut to be 1/4 the wavelength. The other reason for the matching layer is because it is the interface between the transducer and the patient. So you need to use acoustic coupling gel to eliminate any air pockets. We talked about this before. So if Z2 is much greater than Z3, so if this is the matching layer Z2 and Z3 is air, then you're going to get full reflection, if you recall the formula. So Z3 would basically be extremely low because the density of air is not very high. Then you have Z2 with a higher density, higher speed of sound, and basically Ri, which is the reflective index, is going to be equal to 1. So it's going to be full reflection. So you need to use something between the patient and the transducer, and that's why we have the ultrasound gel. As I mentioned, air will attenuate and reflect the ultrasound. And I'm not going to go in too much into this, but just to show you that ultrasound is for sure complicated. It's not a 2D thing, it's a 3D thing. So this is a linear array here. It's two types, basically linear array and phased array. So for the linear array, you can control which elements you want to fire out. Versus the phased array, they all get activated at once. But I just wanted to show you there's it's kind of a special spot, and that's called the focus. And that's mainly where you want your object of interest to be for all imaging. So just to go over some of the beam properties, just to explain that further, focal spot. So I'm not a huge fan of this diagram, but I found it in that article. And basically, as I mentioned, you want your focal spot to be in this area here where the object of interest is. And that's because the software thinks that the ultrasound is being transmitted over this dotted line here. That's what the software thinks. But in reality, the ultrasound is going like this. It's coming in and then moving out. So what you can do is on the machine, you can switch the focal spot. your object of interest to basically be right where the focal spot is. And there's a way to do this on the machine, so you can change it. And basically, when you're changing the focal spot, all you're doing is what the system is doing, is it's just delaying the time between each between the activation for each element. So in this case, if you want the focal spot to be closer, you want to delay the you want to have a larger delay between the activation of each element, as I'm showing here. If you want the focal spot to be further away, then you want to decrease the time between the activation of each element here. So this may not be terribly important right now, but it's important when you're learning about when you're learning about artifacts. So now if we get into like the artifact portion. So again, artifacts are any part of an image that does not accurately represent the anatomic structure present. So the question is, how are artifacts formed? So we had to understand the ultrasound signal and how it's formed. We had to understand wave properties, which we've done. And then where do these artifacts originate from? So we have the transducer itself, which we learned a little bit about, the object being image, and we learned about how waves interact with matter. So this is just a few definitions. I might not use them as much because I don't want to use a term that people are not familiar with, so I'll explain it as I go. But just know, maybe for your board exams, that these definitions exist. So this is a beam width artifact. So basically, the software assumes that the imaging plane is indicated by the dotted lines, as I mentioned before. But the issue is, you just want to look at this object here. You don't really care about this one. But it just so happens that it is in the way of the ultrasound beam. And the software only assumes that you're acquiring an image along this dotted line here. So the way to actually remove this from the image is to go to the system and basically switch your focal spot, just so that you can see this. And it's something that you play around with on the machine, so it depends on what you're looking at. But basically, if you adjust the focal zone to put the object of interest in that zone itself, it eliminates the misplaced echo. And then you also have the side and grating lobes. So basically, these are just additional off-axis low-energy beams that kind of go out to the side. These side lobes are multiple beams of low amplitude that project radially from the radial expansion of the piezoelectric element. So basically, you have like a really high attenuating object here, and it's a strong reflector. And it's in a path that may create echoes. So you have, since these beams are three-dimensional, they come out as lobes. So this beam right here will definitely interact with it. This beam, a portion of it might interact with it, same with this one. And maybe because of scattering, or just the divergence of the beam, it will interact with this strong reflector. And what will happen in the image is that you can see that there's one here. 4 of them will show up. So that's a one type of artifact, and they may not all show up with the same intensity. These may be different intensities. And then you have the Reverberation Artifact. This one is the most common, and I mean when I'm doing ACR testing, just because I can see it between the air pocket and the transducer array with the skin surface. So basically, I didn't really like the diagram that I found in their paper, because it just shows that, you have this basically what a reverberation artifact is that ultrasound echoes are being repeatedly reflected between 2 highly reflective interfaces, and then they go back to the transducer. So you have this, the signal here, this wave that keeps bouncing back and forth, back and forth, back and forth, but eventually it has to go back to the transducer. So that's the only way that you can actually see anything in the image, is it has to go back to the transducer. So the way that I displayed it is sort of like this. You have one wave coming down here, and then it's transmitted through. Then you have a portion of it that's transmitted through, and some of it will reflect, shown here, and some of this will reflect as well. But it's also possible that, you know, if we look at a similar case here, some of the wave will come down here, some of it will be transmitted, and then this will be reflected. Some of that will be will reflect. Some of that will reflect and then go back to the transducer and so forth. So that's what a reverberation artifact looks like. You can see it here clearly in the image. And then over here, these ones are a little bit more spacey, which is good. Sometimes they can show up as a comet tail. So you can see that there's like a highly reflective material here and here, and this huge shadow here. So that's something else to look out for. They also mentioned ring down artifacts. These are also referred to as a comet tail. And basically this has more to do with the electronic processing of the scanner, which converts this continuous sound wave into a series of bands seen as a ring down artifact. So basically, the way that they've shown it is that there's a main ultrasound beam that's encountering a ring of bubbles, and these ring of bubbles are filled with fluid. So the vibration from the pocket of the fluid causes a continuous source of sound energy that is transmitted back to the transducer for detection. And so interestingly, you're probably wondering, why is it going down? The transducer is up here. And that is because it's an electronic processing issue. It's because of the time delay for each one. So what do I mean by that? So you have this beam coming down and interacting with this highly attenuating material here. And some of it is reflected right away, but some of it isn't. And because there is a time delay, the software will assume that the signal came from a deeper area. So that's why, you get this sort of streak that goes downward, because the ultrasound software thinks that it is coming from a deeper area. And that's the same with the mirror image artifact. So basically, this one here creates a reflection of other structures when they aren't really there. So what happens with the mirror image artifact is that you have your sound waves coming down and reflecting, and then you have basically other sound waves that come down here, and then they reflect off this highly attenuating material here, which is similar to what this is, and then you have that reflecting back and forth and then up again. And so basically what the software is assuming is that again, this here is coming from a deeper area, but also interacting with this, and that is why you get this mirror image here. This is what happens over here as well. So basically it's just, there's another artifact here which I'll come back to. Typically mirror image, this is probably the best description of a mirror image, just because it just shows the single artifact. But basically it just thinks that there's another structure here, because the sound waves that have been reflecting off this interface here and this interface here for a little while reach the transducer after a longer period of time. Then you also have the speed displacement artifact, which is similar, except that you have your sound wave that comes down and then goes back here. Then you have this little air pocket here, which when the sound wave is going through will actually slow down, and then it will take longer to actually get to the bottom here and then go back up. So this again is a result of how the software assumes that because the signal took longer to get back, that it's coming from a deeper part that is coming from a deeper area. So you can see that here in the liver. They kind of show a close-up. So basically it's had to come from there's some tissue in the way that has caused the signal here to actually bounce back at different times. Then you have the refraction artifact. So this is an interesting artifact because you have this structure in the way here, and the structure that you want to look at is basically this one, maybe, or maybe you want to look at something deeper. But what ends up happening, and if you remember from before when I talk about refraction, is basically a change in direction of the transmission. So your beam will come down here and then it will be refracted, and you're going to detect this circle in your image, which you wouldn't have detected if the beam had just gone down. I don't like this diagram because this circle shouldn't be here. So, you know, you would, if there was no circle here, then, you know, this circle, then if the beam was to come down, it wouldn't detect anything as it should. And this is kind of similar to what I was talking before. So this artifact here is not only a mirror image, but it's also a refractive artifact, or refraction artifact. And then you have shadowing and transmission. These ones are pretty easy to understand just because, you know, this is how the waves interact with matter. And so basically you have, you know, the sound wave come down here, and most of it gets reflected back to the transducer because this is a reflective interface, and some of it gets transmitted, but then it also, as it bounces back, it will also interact with this and maybe not reach the transducer. So what you're basically left with is this huge shadow here, and this is a shadowing artifact. This is a common artifact as well for, you know, very hyper echogenic structures. And then you have the same thing, well, the opposite with the transmission artifact. So basically you have this like pocket of, this might be a cyst, but it's, you know, there's nothing really attenuating in here. And then as soon as when the beam goes through it, the amplitude will increase, and then it will hit this interface and it will bounce back to the transducer. And so you can see that this part here is a lot brighter as a result. And then you also have posterior enhancement, something similar. So, you know, you have this whole area here where there's pretty much nothing, and then you have this structure here. So as soon as the waves get to this part here, they're just going to bounce back. You're going to be left with this really bright area. And then you have edge artifacts, which basically just occur when the beam is coming down and then reflects kind of off the side here, off both sides in this case. So you get this like shadow, these two shadows at the side. You can see this here with the outline of the kidney, so you kind of see like the edge artifacts here. So it's good for, you know, enhancing edges, but at the same time, like, you know, maybe there's something here that you want to see, or here, and can't see that. So, and then lastly you have transducer artifacts. So basically this is when there's something wrong with the piezoelectric element. You can see that here and here, and then where the arrow is here. So you have like linear transducers and also like curved transducers, depending on what you're trying to image. If you ever encounter these in the clinic, or if you're doing an ACR test, remember to take an in-air image, just so you can see the artifact more clearly. Sometimes artifacts are good. I learned that they can actually be used to detect kidney stones using Doppler ultrasound. I don't know a lot about it, but I'd like to read this paper a little bit more if I plan to talk about it. So just to conclude, artifacts are common in ultrasound. The errors in the image display are unavoidable, and so the ability to recognize artifacts are important. It's a remedy potential for correctable artifacts. The article that I mentioned was strictly educational. Some of the artifacts that I put in this talk were actually not from the article, although I used every artifact that they had mentioned in that paper. So, I would just like to thank you, and if you have any questions, feel free to send me an email. Alternatively, you can leave me a comment in the comment section, and I'll try to get back to you. So thank you again for listening, and be sure to subscribe to my channel, and I hope to see you soon.